Hello and welcome back to Manifolds, the video series where we talk about generalized surfaces and what we can do with them in applications. And indeed, in today's part 57, we will talk about an example for Gauss's integral theorem, which comes directly from physics. And please don't forget that Gauss's theorem is a special case of our generalized Stokes theorem, so we also have an example for Stokes. Therefore, today here you will finally see explicit calculations for this important theorem. However, as always, before we do that, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, you can just click the link in the description to download the additional material for all the videos. And with that out of the way, I immediately go to our motivation, which is the electric field of a point charge. This means our mathematical framework is in R3 and we fix one point, which could be the origin in R3. So this is our point charge and it generates an electric field, which is just a vector field around it. So now all the sketches I use here are in the plane, but you should imagine it in the space. So first here I will write down the formula from physics for this electric field and then we will go to the mathematics. So usually the electric field is denoted by a capital E and it's a vector field in R3. And first we have a constant with physical units, which is denoted by 1 over 4 pi epsilon 0. And just for the sake of completeness, this epsilon 0 is what we usually call the electric constant. But obviously in our mathematical calculations, such constants will be ignored anyway. In the same sense, we will ignore the electrical charge of the particle, which is denoted by Q. The only important thing for us is that the distance between the point charge and the point in space we consider occurs as r. This is something you should know. The further we are away from the point charge, the smaller the electric field is. And moreover, the direction of this electric field is given by the connection vector. So what we have there is a unit vector r hat. So there we have it. This is the electrical field in the space R3 if there's only one particle with charge q. And now mathematically we can simplify that and say that the point charge is in the origin of R3 and all the constants are equal to 1. Hence we get a vector field v from R3 into R3. Hence this sends a point x with 3 coordinates to another vector. And now since we know we want to go in the same direction as the vector x, we can just use x again. The only thing we have to do is to divide it by the standard Euclidean norm of x to get a unit vector. However, since we also want to divide by the norm of x squared, we can just divide by the norm cubed. And there we have it. This already captures the whole idea of this electric field in R3. The only thing we should add here in our mathematical setting is to exclude the origin as a point of definition. This is definitely something you should already note here. We have a nice continuous function, but a singularity at the origin. Hence, we will always have a problem if this singularity lies on the manifold. So let's consider a compact manifold with boundary where the singularity does not lie on the boundary. Indeed, the interesting case would be that the origin lies inside our manifold and let's call it m tilde. I call it m tilde because we will define a better manifold to deal with the problem. You know, we want to apply Gauss's integral theorem, which means we have to remove the singularity in some way. And we will do that by considering an epsilon ball around it. So quite simple, just consider m tilde and an epsilon ball around the origin, which is small enough such that it is completely contained in m tilde. This one now will be our manifold M and it's also manifold with boundary, and as m tilde it should be a 3-dimensional manifold in R3. So you could say here we have full bodies in the space. However, now M has a larger boundary compared to m tilde. Namely because we've added a boundary here in the interior of m tilde. This is important in Gauss's integral theorem because we will integrate over the whole boundary. Therefore, at this point, we should recall Gauss's integral theorem. It's a special case of Stokes' theorem and here perfectly applicable in R3. It's an identity of integrals where we have the divergence of v on the left-hand side and the inner product of v with the outward pointing unit normal vector on the right-hand side. This means in our picture here, we would just put n to the boundary like that. And outward pointing just means if we follow the vector a little bit, we don't hit any points in M. Hence, if we go to the boundary here in the middle, the outward pointing vector would look like this. This totally makes sense and it's important to note for the calculation. Indeed, on the one hand, we don't have explicit information about the unit normal vector field in this general case, but we know the unit normal vectors for the ball. In other words, for points that belong to this boundary here, we can explicitly write down our n. Namely, the direction of n of x should be given by x itself. However, obviously it points in the opposite direction, so we have a minus x for the direction of n of x. And we also have to normalize it to get a unit vector, so we have to divide by the length of x. And there we know it lies on the boundary of the epsilon ball, so we know the length is given by epsilon itself. And that's it. This is the outward pointing unit normal vector for this part of the boundary. Now the other part we don't know, but fortunately Gauss's theorem here tells us how to calculate the integral anyway. And there you already know, this simply works by calculating the divergence of our given vector field. And the definition is quite simple, we just have to calculate 3 partial derivatives. And in fact all the partial derivatives here are quite similar, so let's start with the first one. There we have to take the first component, which is x1, divided by the norm of x cubed. And there we can use that the norm of x is given by a square root. Therefore calculating this derivative just requires the usual product rule. So first calculating the derivative of the first factor without changing the other one, and then the other way around. This means now we explicitly consider x1 squared plus x2 squared plus x3 squared. And now the cube in the denominator means that we actually have the power minus 3 halves here. And now we want to calculate the derivative of that, which means minus 3 halves comes in the front. And we have to reduce the power by 1, so we have minus 5 halves. And moreover, we also get in the inner derivative, which is 2 times x1. And now you see what we could do is to write this in one fraction, so we expand the first one here. So to keep it simple, we can write the norm of x squared for the first part. Hence in the denominator we have the norm of x to the power 5. And this is the same as in the second part, so we have minus 3 times x1 squared. And that's it. This is the result we have for our first partial derivative. In fact, this result is quite nice because it works exactly the same for all the other coordinates as well. The only difference is that for x2, for example, we would get x2 here in the end as well. This means we can use this as a general result and put it into the left-hand side to calculate the divergence. So we have 3 parts in the sum and they all have the same denominator. Therefore we can put them together in the same fraction. The only thing you should not forget here is that this first part also occurs 3 times. So this is our nice result that we get with the calculation from before. And what we should see there is that we have the norm of x squared and that we subtract exactly the same thing. Hence the divergence of v is 0 no matter which point x we put in. The only problem would be the singularity at 0, but we don't have that in M at all. So the immediate conclusion is that the left-hand side in Gauss's formula here is equal to 0. Therefore also the right-hand side here vanishes no matter which manifold we have chosen. This means we can split our integral by using the 2 boundaries we have for M. And obviously one part is the original boundary of our manifold M tilde. Hence we just have one integral for the boundary of M tilde and the other one for the boundary of the ball. And there, to keep it simple, I could say we integrate over the sphere with radius epsilon. And at this point we know this is an integral we can actually calculate because we have the unit normal vector at the sphere. And then we know this immediately gives us a result for the first integral as well. Indeed, the only difference in the two integrals is a minus sign. However, as you might remember, we also have this minus sign in the unit normal vector, so this immediately cancels. Hence, now to calculate it, we just have to substitute our v vector field and form the inner product with the unit normal vector n. And you see, this is not a problem at all, because it's just x with x itself. So what we get is just the standard Euclidean norm of x squared. And this is really nice because it cancels with the denominator, and what remains is just 1 over the norm of x. However, since we are integrating over the sphere, we already know that the norm of x is always given by epsilon. Therefore, we just have 1 over epsilon squared. And then we just integrate the canonical volume form over the sphere, which means we get the two-dimensional volume of the sphere. And this formula you might know, it's 4 pi times the radius squared. And there we have it, our epsilon squared cancels, and what remains is only 4 pi. So you see, the result is independent of how small or large we choose our ball around the singularity. Indeed, the only requirement we had was that the singularity does not lie on the boundary of m tilde, but inside m tilde. And then the result tells us no matter how the boundary of m tilde looks like, we always get out 4 pi for this integral. In fact, here we usually say this is the flux of the vector field through the surface given by the boundary of m tilde. And mapping it to physics again, you would say this is the electric flux. And as before, instead of V, we would use a capital E for the electric field. And in fact, in physics, the notation gets shorter by putting n and the volume form together. There, one just says we have the vectorial surface element ds. It means exactly the same thing, but it's a shorter notation. And now, as you might remember, the 4 pi was already in the definition of the electric field. Hence what remains is only q and epsilon 0. Therefore the result is, no matter how we enclose this point charge, we always get out the charge in the end. So the electric flux through the surface is equal to the enclosed charge. And now it might not surprise you that in physics, especially in electrodynamics, this law is called Gauss's law. For us the name makes sense because it immediately comes from Gauss's integral theorem. Okay, I think that's good enough for today. In the next video, we will look at another special case of our generalized Stokes theorem. I'm looking forward to that, and I really hope I meet you next time. Have a nice day. Bye bye.